Welcome to Train Signal. You're watching a lesson on network topologies. Now in this lesson, we're not only going to go through the various networking topologies that are available, but we're also going to talk about some WAN technologies. Let's go ahead and get started. So to get things started, I'd like to first just go over the definition of a network topology. A network topology is the layout of a network. Now, one thing that I want you to know is that this layout that I'm referring to can be either physical, so we can be talking about the actual physical, how computers and other devices are laid out on the network, or as we'll see in just a little bit here, it can also represent a logical way that the computers are communicating with each other on the network. So what we're going to do here is we're going to actually look at some of these physical network topologies, and you'll see as we go through where some of these bleed over and become kind of like logical topologies. So the first physical network topology I want to go over with you is something called the bus topology. Now the very first thing I will tell you about the bus topology is that it's semi-outdated. Okay, it's not that you never would see the bus topology anymore. You do see it in some places, but for the most part, this is an older topology, and one of the reasons is because of the type of cabling that is typically used in the bus topology. We usually use coaxial cable, and as you learned in the cabling lesson, you don't see coaxial cable used too much anymore. So here on the screen, I've actually shown you an illustration of a thin net coaxial cable, which was a very common cable that was used in a local bus network. Now the next thing I want you to know about the bus network is the way data travels on it. One computer on the network will go ahead and send the data, and that data will go out onto the cable and just kind of branch out in both directions and be sent to every other computer out on the network. Now the illustration that you have in front of you, I will tell you, is just that. It's kind of an illustration, whereas again, going back to the cabling lesson, when we learned about using thin net coaxial cabling, we learned that all the computers that are on this bus network are actually connected using something called T connectors. So I have an illustration here of what some T connectors might look like. The idea is you don't really have a cable branching off of the main cable over to each computer. Now in some cases you could. It was actually possible if you needed to make it happen just because of the physical location of computers. You could indeed add an extra extension cable to get the T connector over to the computer. But in many cases, the one end of the T connector would connect to the back of the computer where the network card, where there's a peg that would stick out. And then the other two is where you would have your actual thin net cable running along, forming that one single long straight bus network. Now another thing you need to know about the bus network is that you must have at both ends of the bus network something called a terminator. The reason you have to have the terminator is because, and if we just kind of go to a little electrical 101 lesson, I know you hear me say that a lot because these are just some of the basics of electrical engineering and how things work. When you have an electrical signal traveling on a cable, when it gets to the end of that cable, the signal bounces back into the other direction. And that signal will just keep bouncing back and forth, back and forth, back and forth until it attenuates away. Okay, attenuation, another term we've talked about before, it's the dissipation of the signal over distance. So we don't want that to happen. Once the data goes out on the cable, and it travels in both directions and it goes across the entire bus and it gets to the end, you don't want that signal to bounce back because now it's just interfering, it's slowing down the network. So the terminator is almost kind of like a form of an absorber. I don't know if that's an actual word, absorber, but the idea is it absorbs that signal. It just takes it and it terminates the signal. Now the last thing I want you to know about the bus network is that a single break in the cable, so if anywhere along the bus the cable was broken, it takes down the entire network. And the reason it takes down the entire network is because what do you have when you break that cable there? You have basically an unterminated end of a bus. And if you don't have termination, you don't have a functioning network. So that brings us to the next type of physical network topology we're going to look at. And this, as much as we talked about the bus being kind of out of date and not something we see used very much anymore, well, here's a topology that is used more than anything else in today's, at least local area networks, and that is the star topology. And this is a topology that I personally think is the easiest one to understand. And the reason is because, well, first of all, if you look at the picture, it kind of looks like a star. The idea is that you have a central connection device. Now, in the old days, this device was called a hub, and so that's actually how I've labeled it here in this diagram, although by today's standards, more often than not, you don't see hubs anymore. We have something called switches, but we'll get into hubs and switches and all that in another lesson. But in the case of having this hub as the central point and then having all these other computers connected to the hub, branching out into what looks like a star, and I will also tell you that you don't literally have to have them set up looking like this. So you don't have to have an office building where you put this hub in the center of a room and you stick the computers out around it forming a star. No, you would just have the computers set up wherever it is that they need to be set up, and they would have cables running into this hub. But the way it functions is like a star, meaning you have a computer who transmits data, the data goes into the hub, and then gets sent out to all of the other computers. Here's the other really cool thing about the star, when I say it's, in my mind, the easiest one to remember and to understand, is that if you had a single break in the cable, it would only take down the one computer that was affected, meaning whatever cable it is, that one cable going out to the one computer, it broke, you no longer have connectivity with that computer, everything else on the network works just fine. If the hub were to fail itself, and again, it could be a hub or a switch or whatever, but if that central device was to fail, well, then you lose the entire network. And that's fairly obvious, because if you don't have that central connection device, well, you're done for. So that's the star topology. The next physical topology I want to talk to you about, and this is where it's going to start to get interesting, because I'm going to talk to you about how physical and logical are going to start to come together here. The physical topology is called the ring. And the idea is that it would be wired essentially the way you see it here, where you have all the computers connected together in a way that they essentially form a ring. And just like with the star topology, it didn't have to be, literal, where in the room that you're in, you set them up in a perfect circle. No, they may be set up wherever they need to be set up, but the way that the cabling is set up, and then the way data travels, as I'll illustrate for you here, is it travels in one direction all around the ring. And the idea is you have the one computer who has data to send, it sends it to the next computer, who then, whether the data was meant for that computer or not, will take it in and then retransmit it out to the next one, so on and so forth, until you get all the way around the ring. If you were to have a single break in a ring network, it would take down the entire network. And the reason why is because the data travels around this ring in one direction. And although you theoretically could, if you kind of want to picture it here, the data could go around the ring and it could hit that end of the broken end of the cable, and then it could bounce back the other way and hit the broken end, bounce back. Even though it looks like it could do that, it doesn't. Once you've broken that cable, you don't have that ring topology anymore. You don't have the data being able to go round and round and round the ring. Now, because of this situation where this single break in the cable would take down the entire ring, the reality is the only primary type of ring network that you'll see is something called a token ring network, which was actually set up as a physical star topology, but would logically function like the ring topology. So the way it would work is, you'll notice here I have what's basically like the star topology set up, but I have the red dots representing the way data is going to travel from a logical standpoint. So it's a logical ring topology set up like a physical. But here's one key difference if we're working with a token ring network. This box that's in the middle, it's not your standard hub. It's actually something called a MAU, which is MAU, Multi-Station Access Unit, or in some cases, it's even an SMAU, which is a smart multi-station access unit. And the difference has to do with some of the functionality and how intelligent it can be about closing off a port if there was a cable broken or a loss of connectivity with one of the computers. But the main thing here that I want you to understand is that this is a star as you see it, but watch what happens when the data is sent out from a computer. The data goes out through the central point to the next computer, and then back in and out to the next computer, and back in and out to the next computer until it's made it all the way around the ring. Okay, so it's functioning like a ring network, even though it's set up physically as a star network. Now, there's another type of network topology called the mesh topology. And I will tell you that there's a couple things about the mesh topology. Number one, as you can see here, the idea is that essentially every computer has a connection to every other computer. And the reason for this is so that you can have multiple paths to get from any one computer to any other computer, so that if one of those paths was to fail, well, you could go another direction. But this illustration that I have for you is not a very good one, because the reality is that the mesh topology is one that you would use not in a local environment, but more in a wide area network type environment. So here is just an example. I just have a picture. I don't know if it's a very good one, but I have a picture of the United States. And I'm trying to represent here that I have 5 different offices in different cities around the country. And then you'll notice that there is a connection between every single office. So every single office you see here has a connection to every other office. And the idea is if you were to lose connectivity with a direct connection, and I'll just use, these are rough ideas, but we'll say that one of these offices is in Chicago and the other one is in New York. If the connection between Chicago and New York was to fail, it doesn't mean that Chicago and New York can't communicate. They would just need to communicate via one of the other cities. So maybe Chicago would have to then send the data down to Dallas and then back up from Dallas to New York. So that's what the mesh topology is. Now, I threw this in here. I do know that it's on the Network Plus objectives if you're looking to take the exam. I don't want you to worry about the specifics of this, but I'll tell you that there are also hybrid versions of these topologies that we were just talking about. In other words, the picture I have here, although I will tell you this is not a very real representation of one, you have these 3 star topologies, and then you have the 3 hubs connected together forming a bus. So again, it's not the most real, but it's just to show you that you can have a hybrid, and you will find out there hybrid versions of the different network topologies. So now let's talk about some WAN technologies. The first couple that I want to talk to you about are kind of a concept here, more so than a literal, and it's the idea of using something called circuit switching versus packet switching. The idea behind circuit switching is when you have an actual physical connection path that is established between a source and a destination. Okay, so down at the bottom I kind of have my cheap illustration again of our WAN network all around the country. But the idea here is that we have an actual path going from, let's say, one city's location, right, where we have an office in one city and then an office in another city. And this path is usually not how I have it illustrated here. It's not like there's like this one big long wire that's been stretched between them. It's actually a series of paths going through a number of different circuits. Okay, and sometimes they'll call them different switches and things like that. But you have an actual established path going from point A to point Z. Whereas with packet switching, we can be much more efficient because data is broken apart into multiple packets, which we already know that that happens anyway. But these packets that the data is split apart into will then take separate independent routes. So whereas, again, I'm kind of showing you the mesh topology. This is that same picture we had from the mesh topology. But the idea is data can be coming from one of those cities, and instead of just all taking that same path over to the other city, they can each take their own path and be sent simultaneously in all these different directions through all these different switches on different circuits and eventually come together at their destination, and then they are put back in order to re-establish the original data at the destination. Okay, so circuit switching is where you have an established, essentially dedicated path, whereas packet switching is we just use all the various paths that are available, and the data is just split apart, going all different ways, and put back together at the end. Now, a few more WAN technologies. Well, we have POTS, which is the plain old telephone service, as well as PSTN, which is the public switched telephone network. Okay, and these are just what they sound like. It's the idea of the telephone network. Okay, you don't really see these used very much anymore, but it's the idea of using a dial-up modem. Something else that we don't see as much today as we did in years past, but we do still see it. I mean, I can tell you that even my office here, we have a T1 line. Okay, so it's not that it's completely out of date, but just for cost reasons, you don't see it as much. You have your T1, or what's also, depending on what part of the world you're in, can be your E1 line, and this is where you have a digital leased line. So you're actually leasing a connection, which is made up of 24 64K, so 64 kilobit channels, which would then provide a transfer rate of up to 1.5 megabits per second. And I will tell you that if you were to go back to the mid and late 90s, this was considered to be lightning fast. If you had a megabit per second of throughput out to the internet or between offices, that was really fast. And the European version, where you had an E1, you had 30 channels instead of 24, which meant you had approximately 2 megabits per second. And I keep talking about this like it's past tense, again, because these are not considered to be high speed anymore, but they are high cost. So that's why I'm talking about it like it's in the past, although they definitely still exist. Now, if that 1.5 or 2 megabits per second was not fast enough, if you were a large enough organization and you needed more bandwidth, especially if it was out to the internet, then you would move to a T3, which is also sometimes referred to as a DS3, or the E3. Now, the T3 is basically made up of 28 of those T1 lines. Okay, so the idea is you're essentially leasing 28 T1 lines, which is a total of 672 channels, giving you a transfer rate of over 43 megabits per second. Even by today's standards, that is considered to be very fast. Now, I will tell you that T3 lines are still not something you're going to see a whole lot of today because the cost involved doesn't match up to that 43 megabits per second. That's still 43 megabits per second to the internet is great, and it's even great between offices. But the cost involved with a T3 line is huge compared to some of these other options that we now have available to us. Now, the European version, where you had an E3, was 512 channels. So whereas the E1 was a little bit faster than the T1, the E3 is actually just a little bit slower than the T3, giving you just a little over 34 megabits per second. But the main thing that I want you to know about these T1s, E1s, T3s, E3s, and I guess I could include DS3 in the mix there, is that these are digitally leased lines that you'll get from a communication carrier. Now, another somewhat out-of-date technology that was used for WAN connectivity was something called ISDN, which stands for Integrated Services Digital Network. And I'm going to tell you point blank, what I have on the screen right now is all you really need to know. Okay, this is not something you see hardly at all. I mean, I'm sure there are some parts of the world where you will find that rare ISDN still being used. But the information I have in front of you is the information you would need for the exam, and honestly, even what you would need to know if you were suddenly thrusted into one of those environments where you were suddenly dealing with ISDN. And that is that it was divided into two different flavors, so to speak. You had basic rate ISDN, which had two 64K B channels, which were for the actual data, and it had a single 16K D channel, which would have the control information to kind of control the connection, control the actual communication. But the idea here was, since you had two 64K B channels, it meant that you had data rates of approximately 128 kilobits per second. Not very fast. And even the primary rate, ISDN, would give you 23 of those B channels and one D channel. And essentially, if you think about it, that's your 24 64K channels, just like we saw a moment ago with the T1 line. So the idea was getting throughput similar to a T1. And this was one of the first ideas that was thrown out there in a way to get T1 type connectivity without having to lease an actual T1 line. Now, a few other type of WAN technologies that are out there are fiber-based WAN technologies. One is called SONET, which stands for Synchronous Optical Network. And you know that this is fiber because it's optical, which means it's using the fiber optics. It's using the light transfer. And then we had SDH, which stands for Synchronous Digital Hierarchy. And with either of these, they were both network technologies designed to carry large volumes of traffic over relatively long distances via fiber optic cabling. Okay, so that's kind of the overall definition there. The idea here is that these are fiber optic networks, large WAN-based fiber optic networks that can take a lot of data over long distances at a pretty good rate. And speaking of those rates, you'll see that the data rates are divided into something called OC levels, or optical carrier levels. And you'll see that even at OC1, we're talking about over 50 megabits per second. So we're already talking about a pretty decent speed. But look at what happens when we get to like OC768. We're at 40 gigabits per second. So we're talking about some real high-speed stuff here. Now, there's also something called DWDM, which stands for Dense Wavelength Division Multiplexing. And the main thing I want you to pull out of this is the words wavelength division multiplexing. The idea behind this is that it's a technology which can multiplex a number of these optical carrier signals on a single optical fiber by using different wavelengths. Okay, and so another way of wording that could be the different colors that are involved in the laser light. By doing this, we also then allow for bidirectional communication on a single strand of fiber. But along with having bidirectional communication, you also have a multiplication of capacity because you're getting multiple communications over that single fiber instead of just the single communication over the fiber. Now, some people think of this, some people, the way they are able to process this is it's similar to something we see in the airwaves, where we talk about something called frequency division multiplexing, which is where you divide the transmission over the airways into different frequencies. Well, it's the same idea, except for you're taking the laser light and dividing it into different wavelengths or the different color of the laser. And the dense WDM is what has been used to, in some cases, replace things like SONET and SDH. Okay, so it's giving us the ability to take it a step further. But I will tell you, here's kind of the bottom line on this, and that is all of these technologies you see, SONET, SDH, DWDM, are very fast, fiber-based technologies designed to take large amounts of data long distances. Now, moving along through some more of our WAN technologies, we have frame relay. The idea behind frame relay is it's a WAN technology where all the nodes are connected through a packet switching cloud. So that's point one, packet switching networks. Point two is the idea behind frame relay is that you pay a base price for an agreed upon what's called CIR, or committed information rate. So you have that base rate, right? You pay a base price for a minimal rate of transmission, and then you pay additional fees as you use more bandwidth and you need faster transmissions. This was sometimes referred to as bandwidth as needed. The idea was, in many organizations, you really didn't need that much bandwidth going on between the two different offices, but there were certain times of the day where you would have bulk transfers. And during those bulk transfer times, yeah, you needed some serious bandwidth, but you didn't want to have to pay for that serious bandwidth all the time because it's only being used some of the time. Frame Relay solved that problem by allowing you to pay a base rate that gave you that minimal rate that was good enough for during most of the day. And then when you had that bulk transfer, you would get that speed that you needed. They would open up those different switches. They would get the cloud going and get all your data going all around and get it to where it needs to be and get it there fast. And you'd pay for that extra speed, but only while you were using it. The next technology is something called ATM. Now, don't think of the ATM as the automatic teller machine where you get your money when you go to, right? You need cash from the bank, you go to the ATM. No. This is asynchronous transfer mode. And again, where I mentioned some of these technologies here, I'm not expecting you to be an expert. This is a little bit of a vocabulary lesson here. It is basically an advanced packet switching network. The things I want you to know is that it used fixed length packets, which are 53 bytes. Okay, it was a concept of by knowing the size of the packet, we didn't have to waste additional header information establishing how big the packet was going to be. So all packets were the exact same size. And I will tell you that although you can get faster these days through compression, when ATM was first introduced, it was able to provide data rates up to 622 megabits per second. And that was considered to be pretty darn fast in its day. I mean, it's still a fast speed, but I'm not necessarily going through these WAN technologies in chronological order. And so I will tell you that when ATM came out, this was lightning fast compared to anything else you could get, especially for the money. Now, there's another WAN technology here, which I'm going to be I'm going to be point blank on this one. I mean, you can tell even just from the screen. This thing called multi-protocol label switching, MPLS. First of all, it's a technique, not a literal service. It is known by some other names as well, and it's just the idea of using something called labeling. By labeling the different types of data, we could get different types of throughput. And I included on the screen an actual link to an article where you can read about this in great detail if for some reason you come across the need to have absolute knowledge of MPLS. But, for the most part, I'm just throwing it on there because if it comes up on the test, know what its name is and know the idea is that it uses labeling. Now let's get into some stuff that we do see, and we see fairly regularly in today's networks. And that is, first of all, DSL, which stands for Digital Subscriber Line, where you can get high-speed internet connectivity using your standard copper telephone wires. So this is kind of cool. Please note that DSL comes in different flavors. You have ADSL, which stands for asymmetric DSL, which is where it allows your POTS, remember plain old telephone service, and data. So basically it meant you could be on the telephone talking and have your data transmitted simultaneously. This was considered to be very cool for many people at home because you didn't want to have to go spend thousands of dollars per month on a T1 line, but you wanted some high-speed access to the internet. So they would just use your regular telephone line. You'd get T1 type speeds, and you could talk on the phone and be on the internet at the same time. It was very cool. We have symmetric DSL, which is essentially the same thing except for that it's not allowed to share the transmission with POTS, so you had to have separate line installed. And then what we see today probably most often is your VDSL, which is very high speed DSL, so I suppose it should technically be VHS DSL, right? But it's not, it's just VDSL. And this allows access to the maximum bandwidth available using your standard telephone lines. But check out the speeds, 13 to 55 megabits per second. I mean, that's some pretty serious speed using the regular telephone wires coming to your house. Some other very typical WAN technologies we see today, and again, a lot of these have to do with, I would say, more of the home and small business environments than the large corporate environments. So we had our DSL, but now we have cable modem technology. And really, the cable modem is what's installed in your house. It's really just broadband cable connectivity is what we're talking about here. It's high-speed internet using the cable service that you get. So if you have cable television, you can get internet from most cable TV providers. And it's pretty good. I mean, I know that mine is very cost effective, doesn't cost me but a few dollars a month, and I get somewhere in the vicinity of about 24 megabits per second access download speed from the internet, and I get somewhere in the area of, last I measured, I think around, anywhere between like 4 and 6 megabits per second upload speed to the internet. So very cost-effective, high-speed connectivity. We have satellite technology, which is not something you see a lot of. I mean, I know there's a lot of satellite TV, but as far as satellite internet, it's primarily reserved for those areas that are so far out in the middle of nowhere that there is no DSL capabilities, there is no cable connectivity. So the only option we're left with is, it doesn't matter how far out in the middle of nowhere you are, you can still get to the satellites out in space, right? So it was just that, the idea of using high-speed internet connections using satellites. And then we have something called the passive optical network, PON. This is also sometimes known as fiber to the premises. The idea behind this passive optical network is it's where you have these optical splitters, and I guess to be more specific, because we're talking passive, they're unpowered. That's part of what makes them passive. These optical splitters that are used to enable a single optical fiber to serve multiple premises. Okay, so you can have this single optical fiber that kind of comes into your neighborhood, and then we can use these optical splitters to go ahead and send this fiber optic signal out to many different homes. So that's the passive optical network, and why it's referred to as fiber to the premises, because it's bringing fiber connectivity, which is fairly obvious here, is pretty good and pretty fast and high speed and all that good stuff. So it brings it to your house. And then we have wireless technology, which is a technology used primarily by mobile users. That's a real big thing today. Now there's two different versions of this. We have something called Wi-Fi, which you'll see Wi-Fi hotspots all over the place, where you can connect with your phone or your tablet or your laptop or whatever it may be, right? You go out to a coffee shop and it's a Wi-Fi hotspot and you get internet through that. Or we could be talking direct through the cellular telephone network. And by today's standards, and this will change over time, and depending on when exactly you're watching this, it may have already changed. But what we're currently talking about today is the use of something called 4G. Right? Being on 4G technology, 4G connectivity. And there are three main versions of the 4G technology. We have one which is called WiMAX, one that is called LTE, and then we have HSPA+. And the easiest way to describe why we have these different technologies is that we have competition in the marketplace through different carriers. And each one of those carriers uses their own technology. So I know that in my area, okay, where I live here, there are multiple carriers, and I know that although it may differ where you're at, where I'm at, Sprint uses WiMAX, Verizon uses LTE, and T-Mobile uses HSPA+. And I will also tell you that each one of them will boast that they have the best technology. Of course they will. It's competition. And there's a lot of articles out there about which one's truly the best. And what I have found, and I encourage you to go do some research on your own and see what you come up with, but what I have found is that there is no answer to which one is best. Each one has its strong points, is really what it comes down to. And you know what the real funny thing is about that? That allows, in a competitive marketplace, for each one of these companies to be able to truly advertise that they've got the best at whatever it is that their technology is best at. And so they all get to claim that they're number one to try to get you to go with them. Now, the last little bit that I want to go over with you here before we wrap up this lesson is it's not so much a specific WAN technology as much as it's kind of related to the idea of WAN connectivity. So we could be talking about topologies or WAN technologies really here. And the first one is something called a VPN, a virtual private network. And you'll see how this all relates. The idea behind a VPN is that it allows traveling users, so people who leave the physical boundaries of your office to be able to connect back to the local network in that office. So let me just kind of illustrate this for you. Here we have a user who is away from the office. They might be at somebody else's office. They might be out at an airport, coffee shop. They could be at home, right? We have like telecommuters. That's a big buzzword these days. People who telecommute, meaning they work full-time for your company, but they never show their face. They sit in their pajamas at home, and they still are able to function in the office, or maybe they're out in a hotel. Okay, these are just some examples that I could give you about where they might be away from the office. But regardless of where they are, they're on their own computer, which I have illustrated here would typically be a laptop, right, if they're a traveling mobile user. But the idea is these traveling users on their laptops will make connectivity to the internet, right, because high-speed internet exists almost everywhere now, whether you're at home or out at that coffee shop, airport, hotel, wherever you might be. And then via the internet, they make a connection with a VPN server in the office, and then via that VPN connection to that server, it is like they have become part of the local area network. So these laptops that you see illustrated over on the left, although they are connecting through the internet, they are actually considered to be like they're in the office. They literally can log onto a domain like they're in the office. They can access resources like they're in the office. Now you might be thinking to yourself, well, that doesn't sound very safe, right? The internet's not a safe place. This is, a very public network. Everybody's out there. Well, these connections are made safe through the use of something called tunneling protocols. And there's two main tunneling protocols that are used. And one is something called PPTP, which stands for the point-to-point tunneling protocol. And I will tell you that that's one of the original tunneling protocols. And then we have a newer one called L2TP, which stands for the Layer 2 tunneling protocol. I will also tell you that there's another tunneling protocol technology called SSTP. I'm not going to go into great detail here, but that has to do with the idea of using SSL technology to make these secure connections. And I will tell you that these tunneling protocols, another way of wording it would be that they are encryption protocols. Through encryption, we create this secure tunnel from that user who's out at someone else's office or the airport, hotel, home, wherever they might be. When they go through the internet, they're going like it's through this secure tunnel that people can't break through, and it's done with encryption. And the very last little piece I want to throw at you here is the idea of a term called VLAN, which stands for Virtual LAN, or Virtual Local Area Network. The idea behind a VLAN is just what it sounds like. You're virtually creating a local area network. And I will tell you that there's two ways of looking at it. One way is that you can take a single physical segment. We talked about topologies and how they can be physical or logical. Well, this is another way of breaking down the physical and logical. You can take one physical segment and divide it logically into two or more virtual segments. Or the other way of looking at it is if you had multiple physical segments and virtually make them act like one logical segment. Now, some of what I'm talking to you right now when it comes to segments have to do with things like IP addressing that we learn about in other lessons, where we have actual subnets on a network, which is also sometimes called a segment on a network, and it all relates to how these VLANs work. So for right now, not the full lesson necessarily on VLANs. I want you to understand the idea of using them and how it relates to what we're talking about. And so that brings us to the end of this lesson, where we started off by going through all the various network topologies, including the bus, the star, the ring, and the mesh. And we even talked a little bit about how there's some hybrid where we bring them together. But then we also talked about a whole variety of WAN technologies. And although I've already kind of mentioned this as we were going through, I really want to put an emphasis that you don't worry too much about being the absolute foremost expert on these WAN technologies. Because to be a successful network administrator, you simply need to be able to have an educated conversation with the WAN technology experts that you're going to be hiring to bring in those services. So that's pretty much it, and I'll see you in the next lesson.